Alright, my name is John Ford, and today I'll be talking about the adiabatic flame temperature of a system. So I'm going to write stuff on the board, and then I'll do a close-up when I'm done. I'll be explaining as I'm writing stuff up there. So first of all, I'm going to start off with our system, and then since we're talking about adiabatic flame temperature, so basically what we're going to do is we're going to toss our air and fuel in, and then going out we will be getting a flame. So since we're talking about adiabatic, this is going to be a steady state system, and then there's going to be no like heat coming out of the sides, potential energy. We're just going to ignore all that stuff. So start off here, the enthalpy in times the dm in is equal to the enthalpy out times dm out. Now again, since this is steady state, the mass will not change, so these terms are just going to cancel out. So we would be left with the enthalpy in is equal to the enthalpy out. Okay, so since we're talking about adding a fuel into a system, here we're going to be adding air as well as a fuel in. So we're going to be using 3 different fuels. I'll be writing code later on to automate the process here. So our 3 fuels that we're going to be using, pretty basic. We got methane, we have ethane, and we have propane. Now we're going to be mixing these with air. So we're going to have our oxygen, and then we are also going to be having nitrogen, since nitrogen is also an air. Now the nitrogen is in a 79 to 21 ratio compared to the oxygen. So we're going to need to put this into the equation. So it would be our left-hand side, and then these are going to be combustion reactions. So we will be getting out carbon dioxide as well as water, and then the nitrogen actually is going to make its way through the system. It's not really involved in the the reaction or the combustion reaction, but since we're talking about, coming back here, so we're going to be starting around 298 kelvins here, and then going out the flame, we'll just set it at 2000. So obviously that's a pretty significant difference. So nitrogen is going to stay in there. So you got CO2 plus H2O. Then that's the same for all 3 of these fuels. However, the stoichiometry is going to be a little bit different for each equation. And then we're going to be adding in the nitrogen on this side as well, still keeping in that 79 to 21 ratio. Now as we do stoichiometry here, 1 carbon on each side here, we got 4 hydrogens, 2 hydrogens, so we're going to put a 2 in front of that, left with 4 oxygens on the right, put a 2 there to equal out. Now, since we're using air, the mole ratio here between, or the moles of the nitrogen, oxygen, are going to be the same, so just transfer that in. Here, 2 carbons, we're going to put 2 carbons there, 6 hydrogens, we need 6 hydrogens there. So this is going to be equated to 7 oxygens. So since this is O2, we're going to do 7 over 2, and then obviously do the same thing for the nitrogens on both sides. Now for the propane, 3 carbons, we have 8 hydrogens, and now we got 10 oxygens on the right. Put 5 there for the O2, 5 from both the nitrogens. So that's going to be our fuel equations. Now we're going to be needing to calculate the enthalpy of each of these fuels, as well as each of those part of the equation. So we got the fuel, which is the organic compound. We got oxygen, we got carbon dioxide, we got water, and we got nitrogen. So for each of these, it's basically going to be the enthalpy of, let's just say, we'll just put compound. So I'll put any compound at 2000, which is our ending temperature, kelvins. It's equal to the enthalpy of the compound at 298. And we're going to have to add in the heat capacity here. Now, the heat capacity will not be different, or it will be different for the compound as the temperature increases here. So the way we allow that value to change as the temperature changes, we integrate it. So we integrate the heat capacity here from 298 to 2000 from temperature. Now, the equation to get the heat capacity for each of these compounds, we're going to be taking from ChemCAD. It's going to be equation 107, so I'm going to pull that up here. So, we have equation 107. I'll get this down. We have equation 107 right here. So that's going to be A plus B times C divided by T, C over T, all over hyperbolic sine of C over T, all that squared, plus D times, I believe that's E over T, all over the hyperbolic cosine of E over T squared. Now this equation is going to be substituted in for CP. However, the equation, I'm going to give a little close-up here, explain some stuff. So, just to reiterate here, so we got our system here, we put our air and our fuel in to get a flame, and then this will work down. Enthalpies will be equal to each other, going in and out. And then when we're talking about specific compounds at the beginning and ending temperature, we have to factor in the heat capacity as an integral from the starting to the finished temperature. And then we do that by substituting the heat capacity equation in, which we get from ChemCAD. And then we will need to use Wolfram alpha here to get an equation, or basically get the integrated equation of this. So I'm going to go ahead and pull up. Alright, so I already have Wolfram alpha pulled up. So Wolfram alpha, so we need to integrate. Let's see, we got A just be AT, so we got C divided by T divided by the hyperbolic sine of C over T squared so that will be our equation there. So we got times C times the cotangent, which will just be the hyperbolic cotangent of C over T plus, here we're just going to, instead of sine, the hyperbolic sine, got the hyperbolic cosine here. And then instead of a plus, since there's a negative there in the integral, we're going to do minus d times e of, is that hyperbolic tangent of e over t. And there we go, that's the integrated equation. So basically what Wolfram Alfred did, integrated this whole equation here into this. And so now that we have this equation, this will tell us for each compound the enthalpy. So now we have all that. I will end this video, and then I'll be making a second video on the code to this equation to automate the process, so you don't have to be plugging in stuff to that very nasty equation. So, thank you.